So now what we're looking at is we're really trying to answer these two questions today. First of all, what does it mean for a function to be increasing or decreasing? And then secondly, how does that relate to the derivative? Okay, so I want to start with these two functions here. One is just our quadratic parent function, and then over there we've got a cubic function. But let's take a quick look here at this quadratic function. And basically, if I have a function that is decreasing, like here, where would you say that this function is decreasing?
On the left side of the line.
Okay, on the left side. And you guys are kind of getting the idea that as we're looking at this, just like we do with slope, we look at it going from left to right. So as we go from left to right here, our function is decreasing. Okay? Now, one way that we can see that it's decreasing is that if we were to look at the points on this function, like negative 3, 8, or not negative 3, 8, negative 3, 9, negative 2, 4, and negative 1, 1, you'll notice here that the y-coordinate is going down. Okay? On the other side, on the other side of this function, you can see that it is increasing. Let me get back to the pen. It's increasing. And again, that's going to be because as you look at the points going from left to right, we have 1, 1, we have 2, 4, and we have 3, 9. And what's happening here is that the y values are increasing, are getting bigger. Okay? Yes?
Well, wouldn't determining whether a function is increasing or decreasing, like, could you potentially look at the function in a different way than left to right?
Not with talking about as increasing and decreasing. No,
Okay,
it's
so
not like we do limit from the left or limit from the right.
Mm-hmm.
That's really the only time when we're doing a limit from the right. That's really the only time when we go from right to left.
Okay.
Now, this also brings to question one other thing, and that is, what's going on here at 0, 0?
Y equals 0. I mean, the derivative is equal to 0.
Okay. The derivative equals 0. That's what...
Well, the x-axis is the derivative.
The x-axis is the derivative, or it's the tangent line. Okay. Are we increasing or decreasing there?
Neither.
Neither. Okay. So for a moment there, it's not going down, it's not going up. That's a turning point. Or we could call it a minimum point. And that's one of the things that we're going to look at more in depth today is these, how do we find these minimum points, or what do they actually do for us? Okay? Or maximum points as well. All right? So, obviously we took a little bit of time with that, but you can, once you get the hang of this, very easily find these different intervals of increasing or decreasing. Now, before we go on and do another one here, let's just let's look at one here. If we are decreasing, we could express this as an interval, and we'd say it's decreasing on the interval from negative infinity to 0. And notice I use a parenthesis, not a bracket, because like we just said, at 0, it's not increasing or decreasing. Okay? It's actually what we would say is stationary. And then we also have increasing. It's increasing to the right of 0, so again we'll use a parenthesis, 0 to infinity, to show that interval there. Okay? So, not too bad so far. So then we have the second one here. And just by looking at it, where are we increasing?
Left to -1, 3. And from 2 to -4 to the right.
Okay, so from the 2, -4 to the right, and from the left all the way up to this point right here. Okay? So we have a maximum point at at -1, 3. And we have a minimum point. And when we're talking about these, we're talking about local, or we could say relative max and min points. Okay? Relative max and min points. Obviously, to the right it goes up to positive infinity. So that, that maximum isn't the maximum for the entire function, but in that general area, it reaches a peak there. So we say it's a local max. But you're right, it's increasing to the left of -1, so from negative infinity to -1, and then also from 2 to positive infinity. And then between these two, it's going down, it's decreasing. So it's decreasing on the interval from -1 to 2. Notice that's not a point, that's an interval. Make sure you look at context when interpreting notation. Okay? Any questions so far?
When would, are there any instances for what we're going to be working with for, at least the next couple of weeks where we would have a closed bracket when we're looking at the, intervals, or no?
Not really. I will tell you this. Depending on what resource you look at, you will see ones that use closed brackets. And it's really just kind of a matter of preference, kind of like with the limits that go to infinity, are they infinity or they do not exist? It's kind of a matter of preference whether people put the bracket or don't put the bracket. Technically speaking, because the derivative is 0, it is not increasing or decreasing there, so I think that the parenthesis is a more precise or more accurate way of doing it, but you will see resources that use the bracket.
Intervals, it's always the x values that,
Yes, for these intervals, you're going to use the x values, okay? Yeah, it's a good question. All right, so one other term that the IB doesn't make a big deal of, but I do want to point out, is just this idea of monotone increasing or decreasing. Now, the word monotone, mono means one, and tone is the sound, right? So if someone is talking monotonely, they're not using any kind of inflection or anything in their voice. It's just one tone the whole time, and it's very, very boring to listen to. All right, very robotic. Okay, when we're talking about monotone increasing or decreasing, we're basically just saying that for the entirety of the domain of the function will be increasing or it will be decreasing. It will never change direction. Okay? Another term that you can use here is strictly increasing or strictly decreasing. You can see here the two examples that you're given are exponential functions. You have an exponential growth and an exponential decay function there. Logarithmic functions fall into this category. Strangely enough, trig function, the tangent function, if you think about it, tangent looks like this. There are points where it's undefined, but it is always increasing. Okay? So there are a variety of functions that are monotone increasing or decreasing. Again, it's not something that IB makes a huge point of, but I did want to point that out to you. There's a term there that you might see as you're looking at different things.
All linear functions would be the same way, right? Or no?
Yeah, actually all linear functions, unless they're horizontal or vertical lines, would be either monotone increasing if the slope is positive or decreasing if the slope is negative. Yeah, that's exactly right.
With exponentials as well.
Yeah, these exponential ones here, all exponential functions would be either monotone increasing or decreasing. Same thing with logarithmic functions. All right, so let's start digging into the math a little bit, okay? Here we have, I've kind of given you the graph and I've given you the answer. I want us to see the math kind of behind the answer, all right? Here we have the graph of the function x cubed minus 3x plus 4. And you'll notice I've labeled on here that at negative 1 we reach this max point, and at 1 we reach a minimum point. So we can tell just by looking that on the interval from negative infinity to negative 1, and from 1 to infinity, we're increasing. On the interval from negative 1 to 1, we're decreasing. So how would we find this on our own if we weren't given or can't find the graph? And obviously we weren't given those intervals. So it's really kind of a three-step process. Those of you guys who like, these little step-by-step directions, you'll like this part. Okay, so first of all, at this point in calculus, if we're not sure what to do, what do we do? Find the derivative, okay? Find the derivative. So we're going to find the f prime of x. And in this case, what is f prime of x?
3x squared minus 3.
Yeah, there we go, 3x squared minus 3. Okay, so that's not bad. The next part, we need to think about the points where that separated the intervals were these max or min points. And we'll look at one other type of point here in a minute. But what was true about the derivative at those points?
It's a horizontal line.
The tangent line was horizontal, so that meant that the derivative was 0. Okay? So I know that f prime of negative 1 actually equals 0. And I know that f prime of 1 equals 0. Now, how do we prove that? Well, that's where step 2 comes in. I wouldn't know the numbers already. I would just have the equation. So what I would do next is solve f prime of x equals 0. Because that's going to give us the values that separate the intervals. Okay, so if I put 0 equal to 3x squared minus 3, I could add 3, divide by 3, and square root, and notice I get plus or minus 1. That's where the negative 1 and the positive 1 come from. That's how I would know that those values right there are where the max or min points are going to be. Okay?
Quadratic equations.
What?
So it's basically a simplified version of like solving for like the vertex of a quadratic equation. Or it's exactly that, just in a different way.
Well, if we had a quadratic to start with, then this process would be a method of solving for the vertex, yes. But in this case, we can now find them max and min points of cubics or quartics or quintics or whatever we want. Or even ones that aren't polynomials. Okay? Now, what we just did is we divided up the domain of our function into 3 different intervals. We have the interval from negative infinity to negative 1. We have the interval from negative 1 to 1. And we have the interval from 1 to infinity. That's what those values just did. Okay? So what we're going to do is we're going to actually test, and this is the third part of this. Test each interval to find the sign of f prime. Notice I don't care about the value of f prime. All I care about is the sign. That will help. If you remember that, that'll help you save some time. Because remember when we were using the quotient rule and stuff, we get these really nasty looking derivatives. Like we might get something like a negative 3 times x minus 5 times x squared plus 4 to the 4th power over x minus 3 squared. Well, if I'm doing this step and that was my derivative, I know anything to the 4th is going to be positive, and I know anything squared is going to be positive. So do I need to plug the value in there? No. All I really need to test is this little piece right here. Saves us a lot of time. Okay? I just plug the different x's into that, and I can figure out is the derivative positive or negative. Okay? Now, our function here is simple enough that we can find the actual values pretty easily too. So, we're going to go ahead and do that. Now, how do we test each of these intervals? Well, you pick a number that's inside the interval for x. So, to the left of negative 1, why don't I try negative 2? If I plug in a negative 2 into f prime, I get negative 2 squared is 4 times 3 is 12. 12 minus 3 is positive. It's positive 9. Okay? But really the thing that I care about is that my derivative is positive. And here's the thing. These intervals are significant because if I know that one value has a positive derivative in that interval, I know all the values in that interval will have a positive derivative. Okay?
But that's not the same thing, right?
Well, let's see. If I have f prime, let's say of 0, 0 is between negative 1 and 1. If I plug in a 0 to the derivative, 3 times 0 squared minus 3 is negative 3. I just showed that everything between negative 1 and 1 has a negative derivative. Okay?
So the sign will tell you like whether the derivative is positive or negative.
Correct.
And then that'll tell you whether it's increasing or decreasing in that interval.
That's correct. Yes. And since you brought that up, notice if f prime is positive, what does that tell us about the function?
It's going to be on the left.
It's going to be increasing. Okay? Because look, if I were to draw the tangent lines, all those tangent lines have a have a positive slope. right? So if my derivative is positive, it's going to be increasing. Where the derivative is negative, my function is decreasing. Because if I drew the tangent lines, I'd have negative slopes. And then the last one, I'll try 2, f prime of 2. 2 squared is 4 times 3 is 12 minus 3 is a positive 9. So it's positive, which means I'm back to increasing. Okay?
So if you were to plug in the value of, like, in the actual range, so if you plug in, like, 1 or negative 1 into f of x instead of a value, like, within it, you'll always get 0, won't you?
Correct, yeah. Well, into f prime.
Yeah, like, instead
If
of
I
plugging
plug
in-
negative 1 into the function,
well, it's not into the function, but, like, here you're plugging in 2, negative 2, and 0, so they're all, like, within the interval. If you plug in the actual, like, value of the interval into the derivative, you'll always get 0.
yeah, because the way we got those numbers was by setting the
Yeah.
derivative equal to 0 in the first place. So yeah. So we just confirmed here that it's increasing on the intervals from -1 or negative infinity to -1 and from 1 to infinity, and it's decreasing between -1 and 1. Okay? Now, I'm going to go to another slide that has a lot of the same information on it, but I want to point out a couple more things and some terminology here. Okay? So we're looking at the same thing. The -1 and the 1, remember we just said those come from setting the derivative equal to 0. Okay? Now, those points have a name. Okay? And they actually have, the points have a name and the values of x have a name. It's important that you pay attention when you're asked for things, that you give what you're asked for, okay? We have critical values, okay? The -1 and the 1 came from setting f prime of x equal to 0, okay? So in this case, x equals -1 and 1 are critical values. Now, there is one other case where we get critical values, and that's the value of x that would make the derivative undefined. Okay? But a critical value is a value of x that makes f prime equal 0 or undefined. Okay? So those are the values of x, the critical values. On the other hand, we have what are called stationary points. If it's a point, that means it's an actual point on the graph. So if I plug -1 into the original function, it was x cubed. What was the original function? X cubed
Minus 3x plus 4.
minus 3x plus 4. So if I plug a -1 in, I have -1 plus 3, which is positive 2, plus 4, that's 6. So -1, 6. And if I plugged in 1, I'd have 1 minus 3 is -2 plus 4 is 2. So I have the point 1, 2. Those are what are called stationary points. And that's ARY. Stationary points. What does stationary mean there?
Not moving.
Not moving. Well, we told you that that's where the derivative equaled 0. Remember, derivative is the same as velocity. Okay? If our velocity is 0, we are not moving. Okay? So that's why those are called stationary points. They're the moment when we are not moving. Now, those stationary points can be classified in 3 different ways. we'll see two of them here. First of all, notice we have increasing and then decreasing. If I have a function where it's increasing and then it starts to decrease, that point where it changes would be what? A maximum. It's a stationary point, but that's what's called a local maximum. Okay? And then over here at 1, it's decreasing and then starts to increase. So if this is at 1, that means the point 1, 2 is a local minimum. Now, why do we use the term local or relative? Well, that's because technically this does go down forever.
Yeah.
Okay, and this does go up forever. But we're saying in an isolated location, there's a peak there, or there's a minimum point there. There's a change in direction taking place. Okay? Now, again, we're learning a lot of terminology in this section. We're going to be using it throughout the week and really throughout the rest of the year here. But one other element or question that kind of comes from this is, are critical values always going to give us some max or min points?
No.
And the answer is no. We have what are called plateau points. Okay? And that happens in the case here we could see of the parent function y equals x cubed. Now you guys know what this looks like. We have 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. We have this parent function for the cubic function. Okay? Now, if we go through the process that we just looked at, we find the derivative, 3x squared. We set it equal to 0. What would make that equal 0?
0, 0.
X equals 0, yeah. So right here, the point 0, 0 is the point where the derivative equals 0.
Yeah,
Yeah.
but isn't the cubic function strictly increasing?
Except for at 0. Because at 0, what did we just show?
Derivative is 0.
The derivative equals 0, so it's not increasing or decreasing there. That's why we call it a plateau point. There's a moment, a plateau in geography is just an area of land that's raised up, but it's flat. Okay? So a plateau point is a place where the function momentarily flattens out, has a derivative equal to 0, but the derivative does not change signs. If I did a sign diagram, I'll be with you in a sec. If I did a sign diagram for this, if I plug in negative 1, I have 3 times negative 1 squared is positive 3. So that's positive. I'm increasing. If I plug in positive 1, I still get positive 3. So it's still increasing. When you have no change in sign, that means there was no change in direction. Okay? There's no change in direction taking place here. Okay? So that means it levels off for a moment, but then continues on. Okay? That's the basic idea of how we can use the equation to tell things about the graphs and classify those critical values or those stationary points.
So when you plug in 0 to the derivative for the first time and you get just one answer, does that mean you only have 2 intervals?
Yes.
Okay.
Yeah, I got 0. So yeah, we had the interval from negative infinity to 0 and then from 0 to positive infinity.
Okay.
So.
So since